Right, we're going to go over the Riemann sums practice sheet that I gave y'all. Right, for our first problem, we have a very traditional multiple choice question here. And notice that we're told that we have 50 liters of oil at time t equals 4. And oil is being pumped into the tank at a rate r at t. And do take note that we have r at t, and that is in liters per hour, and we are measuring in time t hours. Now, skimming through the problem, they want us to use a right Riemann sum with 3 subintervals and the data to find an approximation for the number of liters of oil that's in the tank at time 15 hours. So with the right Riemann sum, if we remember, with the right Riemann, and I'll just very quickly draw, and of course my drawing is really horrible, but with right Riemann, we start with the rightmost corner of our rectangle, and that determines the length of the rectangle being drawn. So if we want to set up this with a right Riemann, it's usually a good idea to start over with the rightmost. So here with our rightmost, that we would start over here. And of course up here, this is representing the x-axis, and this would be talking about the y-axis if we were back to our traditional picture of things. And so to set up this problem, then we are going to go back and say, well, the length from 12 to 15, from here to here, is 3 times the height is going to be determined by the rightmost, so it's 5.6 plus, and then again, let's determine the width is going to be 5 times, and we use our rightmost to determine the length, and then finally plus, here the difference there is 3, chopped off that 7, poor 7, times 6.2. And so notice that's how we would go ahead and set up our Riemann sum. So let's find what this is going to add up to be. And we should have a sum of 64.9. Now, we have to be careful with this. Let's go back and remember what's the question asking. And that's going to be, let's see, use the approximation at time 15, how much oil is in the tank. Now be careful, don't choose A. Even though our answer matches A, go back and remember, they told us that we had 50 liters to start with, and now we've pumped in from 4 hours to 15 hours, we've pumped in an additional 64.9. So we do have to add 50 back to that, and so that's going to give us 114.9. So that is answer choice C. Okay, for our next problem, we're given a table of values for the continuous function f, and we're told that f is increasing, so that's pretty important there. F is increasing over that interval from 0 to 3. Which of the following could be the value of the integral from 0 to 3 of f of x? So we need to remember that if we're talking about could be, and we don't have our function per se, so it's kind of hard to get that exact value, but let's do a left Riemann sum and see what that would consist of. So if we do that from 0 to 5, then, and again, keep in mind this is your x and y axis. So your left Riemann sum, your distance 0.5 times your leftmost y value plus, and we would continue this, 0.5 times 4, because all of these distances are 0.5 apart. And let's see, 0.5 times 18, 0.5 times 28, and finally plus 0.5 times, get this pen, 0.5 times 40. And so if we add up all of these different values, we're going to see that we ended up with 50. And again, keep in mind, we're just taking half of all those. So 50 would get us our left Riemann sum. Now, our function f is increasing, so a left Riemann with an increasing, this is really an underestimate. So I know it can't be A. That's an underestimate. So now let's talk about doing a right Riemann. So a right Riemann sum, again, we're going to have all of the same values, except for we will not be starting with 0.5 times 0. We're starting with 0.5 times 4 plus, and again, we go through all of these numbers, 0.5 times 10, 0.5 times 18, plus, and let's see, we've got to slide my screen over here in a minute, 0.5 times 28, plus 0.5 times 40. And then the big difference here, we've got 0.5 times 40 plus, and then 0.5 times, and again we need to include our rightmost, which is going to be 54. And if we go through and find that value, this value is really going to end up giving us, let's see, adding up all that, it's going to give us 77, which again, that is an answer choice, 77. But remember, with a right Riemann and an increasing function, this is going to be an overestimate. So I think we've just about pinpointed where this answer should be, because that's an overestimate. Here's an underestimate. So 62 could possibly be the value. Okay, for this problem, we have a traditional water being pumped into a tank. And I'm not going to read all of this to you. I do encourage you to look to see that this function is differentiable, therefore it is continuous, and it is decreasing over the interval from 0 to 8. So those are things that we need to know. First thing, they want us to estimate r prime at 2. So r prime at 2 is approximately, and remember we need to go up here and pinpoint really where 2 should be, and it's going to be between r at 3 and r at 1 over 3 minus 1, and so we're going to get 950 minus 1190 all over 3 minus 1, and with our free response you are welcome to stop here, and we need to find our units, and that's going to be liters per hour, or you can say per hour squared. Either would be correct. All right, and for grading purposes, this was 2 points. So it's 2 points that I want everybody to get. Now we're going to use a left Riemann sum with 4 subintervals. To estimate the total amount of water being removed from the tank over 8 hours, and then you need to discuss whether or not this is an over or underestimate of the total amount of water removed, and you have to give a reason for your answer. Now please do not write a flippin' novel here, because AP readers are not going to be really interested in that entire thing. You be short, sweet, straight to the point. So let's see if we can approximate this value. So let's see, we're going to go through, and since we're doing a left Riemann, remember you are finding that's going to be the difference in our x's, and then times our leftmost will give us the height of that rectangle. So let's see if we can go ahead and write that out. Let me slide up my paper here. All right, so we're going to have 1 times, because that is the difference in our t values, times 1340 plus, and then our difference, we're going to have 2 times 1190 plus, and let's see, from 1 to 3, and then we're going to have 3 times 950 plus, and then 2 times 740. All right, and so let's see, what is that value going to be? And we could really, I would imagine, just to stop here. If we continued on, that estimate would be 8,050. And that would be liters, because we're talking about the amount of water. All right, and so now let's talk about, well, is this an overestimate or is it an underestimate? Well, my function was decreasing. So let's talk about this estimate here. And again, go through and use your problem itself. So you're going to say this estimate is, and if my function is decreasing and I'm using a left Riemann sum, then we're going to have an overestimate. Again, that's a left Riemann with a decreasing function. So this is an overestimate. And again, why is it an overestimate? Because, and think about your function. And what was our function's name? It was r, because r is a decreasing function. About to run out of room. All right, and so let's see how many points this was. So you got a point for the left Riemann sum, setting that up. You got a point for your estimate, and then you get a point for your final answer. So this whole part was 3 points. So that's a pretty good amount of points to get from this. Okay, another great free response question. Johanna jogs in a straight path, and they give you all kinds of nice little stuff. You've got, let's see, a velocity. Velocity is given by the differential function v. Selected values, and so the first thing we need to do is estimate v prime at 16. So let's go ahead and get that out of the way. So v prime at 16 is approximately, and again we're looking through here, and 16 is between 12 and 20. So let's see, we're going to have v at 20 minus v at 12 all over 20 minus 12. And so v at 20 to 40 minus 200 all over 8. And so my approximation here, and let's make sure we include our units. So our units are going to be meters per minute squared. So let's make sure we include that. So meters per minute squared. And that's 1 point for this question. All right, so our next problem tells us to, using correct units, explain the meaning of the definite integral. And notice we are integrating from 0 to 40, the absolute value of velocity. And we need to talk about it in the context of the problem. So let's do that first. So when we're talking about the integral, and let me get this situated here. So the integral, my screen's freezing up, folks. Sorry, hang on. Work with me here. Patience, please. Woo! All right, so we have the integral from 0 to 40, the absolute value of v at t. That is going to be talking about the total distance, is the total distance. And who is it about? That Johanna, or however you wish to say that. Johanna jogs Okay, and let's see, how long did she jog? Over what interval did she jog? So let's see, is the total distance Johanna jogs, and well, our intervals are endpoints, right? So over jogs, over the time, and we are from 0 to 40. So, and it was 40 minutes. It's always good to keep those units. So that's talking about her total distance she traveled over the time frame from 0 to 40 minutes. And that's really all it's talking about. So now our next part tells us to approximate using a Riemann sum with 4 sub-intervals from the table. All right, so now we're going to approximate her distance traveled. So in doing that, let's see, we're going to have our integral from 0 to 40, the absolute value of v at t. dt is going to be approximately, and again we're using a right Riemann sum, so that means our rightmost will be determining the length of the rectangle. So the first we need to see, well, what's our time frame? Well, the time frames from 0 to 12 is for the first, so from 0 to 12 is 12 times. And then, let's see, we're talking about absolute value here. So the absolute value of v at 12, because we're doing a right Riemann, we need our right endpoint. So don't use 0, use 200. Plus, and then for our next time frame from 12 to 20, that was 8 minutes. And the rightmost there would be 240 plus, and then our next time frame is going to be 4 minutes. Now, and again, on this one, though, we have to be careful. It is 4 minutes, but it's going to be negative 220, but I'm talking about a total distance, so I need the absolute value of that. So that's going to give me positive 220. And then the last one we need plus, and the time frame difference from 24 to 40 is 16 times, and then her velocity at that time was 150. All right, so there's our approximation. So, and if you wanted to go ahead and add up all of that stuff, you would get 7,600, and it's meters, because you're talking about her distance. And that was a total of 3 points. All right, now we have a part C. For this one, Bob is riding his bicycle along the same path, and for the time frame from 0 to 10, Bob's velocity is measured by, and they gave us a nice, neat little cubic function here, and t is measured in minutes, and b at t is meters per minute. Find Bob's acceleration. So Bob's acceleration here, well, we were told that this is Bob's velocity. So yay, acceleration, we know we are going to find the derivative. So b prime at t is going to be 3t squared minus 12t, and I want b prime at 5. So that's going to give me 3 times 5 squared minus 12 times 5. So that's going to give us our velocity. And let's see, if we go ahead and figure that, that's going to be what? 75 minus 60, so 15. And let's think about what would our units be. Well, let's see, we're talking about acceleration, and it's meters per minute. So this is going to be meters per minute squared, isn't it? So keep that in mind. We always want to make sure we have the right units here. And now, based on, let's see, part D, we have, based on the model, based on the model B from part C, find Bob's average velocity. Now, this is talking about the average value. This is his average velocity. So I want the average value of my given function. So the average value of this is going to be our formula. We're going to integrate 1 over b minus a, the integral from a to b of my velocity function. Oh, and our velocity function has a different name. That velocity function was what? B at t. Okay, so there's our game plan. So we want to find his average velocity from 0 to 10. So that's going to be our b minus a is 1/10 from 0 to 10. And we are integrating our function that we had. So t cubed minus 6t squared. And let's see, and plus 300, I've lost my function, plus 300. All right, so that's our function that we need to integrate. So we're going to have 1/10 times, and so that's going to be t to the 4th over 4 minus, and let's see, that's going to be 6t cubed over 3 plus 300t, and it's going to be evaluated from 0 to 10. All right, so let's continue on and see if we can't solve this. So we're going to be substituting in 10. Well, and very good that the other endpoint is 0. That's going to make things a little bit easier for us. So we're going to have 1/10 times, and let's sub in 10. So I'm going to have, let's see, what's that going to be? 4 zeros, so 10,000 over 4 minus the other is going to be 2,000 plus 3,000. So we're going to have to multiply that by 10 also. So plus 3,000. All right. And there's going to be our answer. So this was another 3 points here. You got a point for the integral, a point for your antiderivative, and a point for your answer. All right, the traditional zoo problem. So, and y'all can read the problem yourselves. Y'all read through. We are told that our function is differentiable, so therefore we can say something about it being continuous. Now, the first thing they want us to do in part A, we need to use the data in the table to approximate the rate in hundreds of entries per hour at which the entries are being deposited at time t equals 6. So we need to estimate here E prime. So we're going to have to estimate E prime at 6. Because again, we're approximate the rate. So here, that's going to be approximately. And so again, right up here. So I'm going to have, let's see, that's going to be E at 7 minus E at 5 all over 7 minus 5. Do make sure you show them this quotient. And so you're going to get 21 minus 13 all over 7 minus 5. And that's going to be our units, and they told us right here, it's going to be hundreds. So we've got hundreds of entries. I'm going to slide over the screen, sorry. So hundreds of entries per hour. All right, so that again was going to be 1 point for getting that. So again, everybody, y'all do your best to get that 1 point. Now we're going to get to use a trapezoidal sum with 4 subintervals, and we're going to approximate, and notice it's the average value of E at t. So we need to approximate this. And then using correct units, explain the meaning that we just found. So it's important for us to realize this is talking about our average value, and we know that because it's 1/8 times our integral. So I know that is our average value. So let's see if we can't set up, and I'm going to erase what I had up here. so it's out of the way. And let's set up our trapezoidal sum. And again, just like how we had to remember the side lengths, they were really coming from our y-axis. When we drew this out, this part here, we're really talking about base 1, base 2, and then so forth. So do keep that in mind. And this up here was our height. So whenever we start approximating, so we have to really be careful with what we set up here. And this was a calculator problem, so we would need our calculators here. We would have 1/8 from the integral from 0 to 8 of e at t dt is approximately. So we need to find the height, which is the difference here. So that's going to be 2 times, and then the sum of the bases. And then, of course, we'll have to go back and divide all of it by 2. But here we can go back and say, well, the sum of the bases is 0 plus 4. And then all of that, we need half of that, plus. And then we go on to our next one. Well, what's the height difference here? Well, that height difference is 3 times the sum of the bases, which is going to be 4 plus 13. And again, divide that by 2, plus. And we're going to continue. Well, the height difference here between 5 to 7 is 2 times the sum of our bases, which is going to be 13 plus 21. And again, divided by 2, plus, and then finally we do our last one. So we have a height difference of 1, and then it's 21 plus 23, and all of that is divided by 2. Now we can number crunch that, type that in our calculators, and we should get, and I am like completely out of room, gracious. So I should get, once you type all that in, 10.687. And so that's going to be, if we explain this in the context of the problem, again, that was your average value. And tell us, what is the average value of what? Well, it's of, well, what was our function? So it's the average value of e at t, which e at t was the average number of hundreds of entries in the box between 0 and 8 p.m., which 0 was at, and it tells you up here, 0 is at noon to 8 p.m. So again, use your problem itself to help you with the wording. And again, there's your hundreds of entries from 0 or noon to 8 p.m. for your E at T. This problem was a total of 3 points, and you got a point for each part that you've set up, and then a point for your explanation. So that was a total of 3 points. All right, for our next problem, we're told that the rate at which water flows out of a pipe in gallons per hour is given by the differential function R. So again, we're given differential, so we know then it is continuous. And now we need to use a midpoint Riemann sum with 4 subintervals of equal length to approximate this value. So to approximate, we have from 0 to 24, and it's going to be R at t dt is approximately. Now we're using a midpoint with 4 subintervals. So the midpoint is exactly what you think it would be. We're going to look from here to here as a time frame of 6, but we're going to use the midpoint to determine the actual height of that rectangle, which is 10.4. So here we're going to have 6 times 10.4 plus, and again from 6 to 12 there's another time frame of 6 times, and what's the midpoint here is 11.2 plus, and again same process over and over and over. So their next length again was 6, so that was pretty nice. Plus, and let's see, that's going to be 11.3 is the midpoint there. Oops, 6 times. Sorry, my crack's wearing off for today. I have to get me some more. 6 times, what was that midpoint? I lost it, 11.3. Plus, and our final from 8 to 24 is another 6 times 10.2. So there's how you set up your midpoint Riemann. And so let's see, what would that give us if we added up all that? And this would be calculator. So if we go through and add up a bunch of stuff, then that's going to give us 258.6 gallons. And so that, just coming up with all of this, is going to give you 2 points. You get a point for setting up the Riemann, and then they gave a point for your solution. So that's 2 points. But then it also wants us to, using correct units, explain the meaning of your answer in terms of the water flow. So this is an approximation to the total flow. And how much water was it? It was gallons. So the number of gallons of water, and gosh, what was our time frame? Our time frame was, oh, there it is, from 0 to 24. So it's over the past 24 hours. So that's an approximate amount of total waterfall in gallons over 24 hours. And with that explanation, that gives you 1 more point. So that was a total of 3 points if you include your explanation. All right. So let's look at B. Is there some time t over the 24 hours so that r prime at t equals 0? Well, we were told that, let's see, we were told that r is differentiable. So let's go look and see. The way that would have to happen, if we get r prime to be 0, then we've got to have some stuff repeating. So let's see, do I have a time frame to repeat? And it looks like I do. Let me change color so we can see where is that time frame repeating. So at 0, notice we have the hour 0, and gallons per hour is 9.6. And then if we scroll through our answers, we've got it again here. So 24 hours, and we have another 9.6. Now you can either use Rolle's theorem or mean value theorem, but I would use mean value theorem. It's just pretty good run of the mill. Now, so is there some time t between 0 and 24 so that r prime t equals 0? And so yes. Now you don't write just yes. That's not going to earn you anything but loss of time. So we've got to justify our answer. So in our justification, you have to state that since we were told, what's the name of our function? R at t. And so r at t is differentiable. So r at t is continuous. Please make that statement. And don't abbreviate like I am. It's just I am really running out of space. You will have plenty of room to write it out. So r at t is differentiable. So r at t is continuous. And we noticed that what were our two values that were the same? R at 0 is equal to, because we saw that, and r at 0 had the same value as r at 24. Okay, so by the mean value theorem, there exists. So, and we can just finish out the problem. So there exists. What does there exist? Well, that's what we were looking for. So by the mean value theorem, there exists a time t, and where is that t? Right here between 0 and, so there exists a time t, and note where that t value is. It's between 0 and 24. 0 and 24 so that r prime at t equals 0. All right, and we knew that we had to use mean value theorem because we were talking about r prime at t. Now, if that prime was not there, just some value r at t equals 0, then most of the time you need your intermediate value theorem. Now, I'm not going to say every time because the problem could be a little bit different. We could have been looking for something else. So be careful with that. But most of the time the mean value theorem, especially if you're looking for r prime at t or whatever prime, then your mean value theorem is going to be the right one. So apparently Ben rides a unicycle. That's great. And we are going to notice we've got all kinds of stuff. We've got Ben's time. We've got B at t, which is going to be probably his distance. And then we've got V at t, which is going to be Ben's velocity. Yada, 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 right? So first thing, again, we've got to find Ben's acceleration at time t equals 5. So remember, to find acceleration, we need the derivative of velocity, but we are approximating. So again, we can say V at t, well, and we know what time is 5. So V at 5 is approximately, and so we need to go find, well, okay, let's see, where is 5 going to be? It's between 0 and 10 most days. And so here, the way the chart is, be careful. It'd be really easy to pull the wrong values here. So here, V at 5. Oh, I've already messed up. Guys, goodness, sorry, I'm pooped. It's A at 5. It is approximately V at 10 minus V at 0 over 10 minus 0. And so let's see, V at 10, so that's going to be 2.3 minus 2.0 all over 10. So there's your approximation for his acceleration, and we need to indicate our units of measure, and so that's going to be meters per second squared, or meters per second, either that you wish to write. All right, so for our next one, part B, using correct units, interpret the meaning of, hey, this is very similar to the one we just did. So we're talking about our total distance that Ben has traveled over the time frame from 0 to 60 seconds. So we already know pretty much what to write there. So that's pretty nice. So let's go ahead and do the meaning of our integral. We can go ahead and get that taken care of. So from 0 to 60 of the absolute value V at t dt is the total distance. So total distance in meters. And who is it? Let's see, that Ben. And let's see, Ben rides over the time frame. So what was our time frame? From 0 to 60 seconds. All right, there we go. So now we have what the meaning is, and now we need to find, let's see, use a left Riemann sum with the subintervals indicated by the data. And so let's go ahead and see. Well, let's set that up. So we've got a left Riemann, oh gracious. All right, so we've got a left Riemann sum. And so we're going to say the integral from 0 to 60 and the absolute value of V at t dt is approximately. And what is it approximately? Well, let's go through and see if we can figure out what we're going to have. Well, the first one's going to be 2.0 times 10. The next one is going to be plus 2.3 times 30, plus the next one 2.5 times 20. And when you chunk all that in your calculator, that's going to be 139 meters. All right, and that is going to give you 2 more points there. So, yay, woohoo. All right, and oh, I didn't give you the point value. That first one was 1 point there. All right, so now let's go to the bottom part. And let's see, what is it asking me for down here? For part C, so between 40 and 60 seconds, must there be a time t when Ben's velocity is 2 meters per second, and justify your answer. So let's see, let's see what we would get here. Between 40 and 60, must there be a time? Well, we know we're differentiable and we're continuous. So let's see. If we're talking about velocity, that's the derivative of his position. So let's see, what is his position at 60 and his position at 40 over 20? So let's see, be at 60, if I can find that, be at 60 is 49 minus be at 40 is 9 all over 20. So we do get to, what is that going to be, meters per second. So yeah, but now let's see, we've shown this, so I'm sure we have to justify our answer. So let's see, this again would be a mean value theorem, because we're really estimating or approximating a velocity. So let's see, so yeah, by the mean value theorem, there must exist a time t. My handwriting is getting horrible. Sorry, folks, I am tired. There must exist a time t. And that time t has to be between 40 and 60. So that v at t equals 2. Yay, we got it finished.